Okay, now that we are experts on knowing the stable part of the carbon cycle on geologic timescales, the weathering timescales, and the instability of the carbon cycle on glacial ice age timescales. Essentially, it provides positive feedback during the glaciation and deglaciation. Obviously, all of this background knowledge is to go towards understanding what is happening now and where we are headed, because we are perturbing the carbon cycle in a massive way by burning fossil fuels and land use change and so on, cement, steel production, to produce lots of carbon dioxide. And we must know the climate sensitivity to the change in CO2, as well as whether the carbon cycle is going to be having a negative feedback or a positive feedback, stable or unstable. I didn't explicitly say it, but generally systems with net negative feedback are stable, like the thermostat, for example. You set it so that if temperature gets warmer, AC kicks in and temperatures go down. If temperatures get colder, then the AC switches off and then temperatures come back up. So this is a negative feedback. And of course, you know what the positive feedbacks are in terms of increasing temperature, releasing more CO2 further increasing the temperature, and so on. So here the carbon cycle at present is acting to dampen the climate change from fossil fuel CO2 by absorbing the fossil carbon into the ocean and the land biosphere. What accumulates in the atmosphere is obviously what remains after land and ocean have taken it up. There are reasons to fear that on longer time scales, say by the end of the 21st century, which is a horizon we are always looking at in the IPCC projections, warming may drive carbon out of soils and the oceans into the atmosphere, amplifying the climate change directly caused by human CO2 release. So we will go through the various fossil fuel emissions and some ideas on what we are already seeing and what we expect going into the future, especially 21st century, and then how this slug of carbon we are putting in now at a very rapid time scale, since industrial revolution is going to equilibrate, and what time scales that's going to happen. This is the canonical poster child for our emissions. Charles David Keeling started it in the 1950s based on the advice from his graduate mentor, graduate advisor, Roger Avell. Mauna Loa, which because CO2 is a inert, long-living, well-mixed gas, you can measure it at 1 or 2 points in each hemisphere to get the hemispheric concentration very precisely and accurately. This is the easy part of the whole business, right? So here is something that started at 1750 at about 280 ppm, coming out of the last ice age from 180 to 200 ppm, as we have seen several times. And the agricultural activity, deforestation, population growth, industrial revolution, coal burning, and so on and so forth has been increasing it, and more recently we are accelerating it. And I think you already heard several times in several places and courses that this up and down every year is the breathing of the planetary biosphere. So when sun comes into the hemisphere, photosynthesis kicks off and there is a drawdown of CO2, especially the northern hemisphere, which has a lot of land. And during the fall winter months, leaves fall, and then there is a re-release of carbon dioxide. And if you remove that seasonal cycle, you see this steady increase in carbon dioxide. Just like during the glacial, interglacial times, we need to know the CO2 change and some isotopic signature to be able to say where the CO2 is coming from. Obviously, most of it is coming from fossil fuel burning, and there are isotopic signatures associated with it, which we said include things like C14 and C13, for example. The fossil fuel we are burning is previously photosynthesized hydrocarbon, which would be deficient in C13. So if we put in so much CO2 from the C13 deficit carbon source, then that's going to show up in the atmospheric carbon dioxide as well. Okay, so you see some evidence of that here from the corals of Arlington Reef in the center of the Great Barrier Reef of Australia, and you can see that over this period of almost 2 centuries you have delta C13, especially in the 20th century going into the 21st century, showing a fairly significant and systematic drop in delta C13. So it's going to get more depleted because you're putting in more of the CO2 from previously photosynthesized organic matter. So very quick check, and there are other ways to do this as well to show that in fact the CO2 we are increasing is not from the natural cycle, it is from digging up fossil fuels and burning them. There is also a reduction in oxygen, as we remember. Let's touch a little bit on the evolution of CO2 in the atmosphere since the end of the last glacial maximum. So looking at this figure first here, we're looking at methane and we are looking at CO2. These are of course from Antarctic ice sheets, looking at the bubbles. We were in the peak of the last glacial maximum till about 20,000 to 18,000 years ago. So you can see this flat line here, the CO2 concentration hovering between about 190 and 200, which we have already talked about. And then it started to increase as the glaciation terminated, with a couple of hiccups like the Younger Dryas and the Older Dryas and so on. And throughout the Holocene, CO2 has increased, and by about 10,000 years ago it had reached a value of about 270, and then it continued to 1750 at to 280 ppm, and then Industrial Revolution took off, right? So let's ignore methane for a moment, and because there are changes in wetlands, peatlands, permafrost, etc. as well. Let's look at the delta C13 CO2, and you can see that there are interesting signals there. You have to explain basically the potential source of carbon which would give you this depletion of delta C13. Remember, we went through the same exercise for the glacial or ice age period, and we basically concluded that the delta C13 signatures, which was deficit by about 0.3 parts per mil, couldn't be explained so much by terrestrial carbon. It had to be done terrestrial organic carbon synthesis. It had to be done by ocean inorganic carbon in the largest part. And we looked at things like solubility increase because of colder temperature, pH changes, biological pump changes, and what else did we look at? Circulation changes. Same thing has to happen here, and of course the debate still goes on as to where that additional CO2 came from. And you can see this one study here showing the peatland carbon, vegetation carbon, and soil carbon at 18 kiloyears, so just before deglaciation. And you can see that the relative amount in the soil carbon increases here almost by double, so 100% by the present natural CO2 levels, which means a lot of buried soil carbon got released corresponding to the change in delta C13. These numbers are constrained by delta C13 using modeling, other isotopic evidences, etc., etc. Vegetation carbon changed as well by almost more than 2.5 times, and peatland carbon got released because of the warming associated with the deglaciation. Okay, so this exercise has to be done also for the future, the present carbon cycle, as well as for the future, knowing what CO2 we are putting in and what kind of feedbacks we are going to have in terms of changes in the soil carbon, vegetation dynamics, of course glacier melt, and ocean carbon cycle. So we'll look at ocean uptake, land uptake, and try to explain whether we can understand the state of the carbon cycle going into the future, whether it's a going to be a positive feedback or a negative feedback. Is it going to be stable or unstable? Okay, that's the main goal of this chapter.